Good afternoon and welcome to RTDology Online, Burns Engineering's web-based training series. I'm Jeff Wiggin, National Sales Manager, and presenting today will be Bill Bergquist, Senior Applications Engineer. Today's presentation, Thermowell Selection and Application, is part of our continuing series of training modules designed to help you better understand temperature measurement and achieve your measurement goals. If you've joined us for our previous sessions, we'd like to welcome you back. If this is your first time, welcome. And when you get a chance, do check out our previous presentations on the RTDology page at burnsengineering.com. Before we get started, just a few housekeeping items. To respect everyone's time, we'll make every effort to limit the presentation and Q&A period to 1 hour. We highly encourage questions, so please go ahead and type them into the QA section or the chat box on your screen and send them to host and presenter. We'll attempt to answer as many as time allows. Today's session is being recorded, and we will provide session notes and a link to the recording to all participants as soon as they're available. Typically, this takes about a week, and we'll get those sent out to you. If we don't get to your question or you need some additional assistance, there will be contact information at the end of the presentation, and you can go ahead and contact us directly. And finally, our goal is to answer your temperature measurement questions and challenges. We've built our RTDology series around commonly asked questions and issues. However, if you have a particular topic you'd like to have us consider, please give us a call and we'll see what we can put together for you. So that covers the housekeeping. So without further delay, here is Bill Bergquist to help explain Thermowell selection and application.
Well, good afternoon, everybody. Today what we're going to talk about is how to select a Thermowell, some of the different materials and surface finishes, immersion lengths and their importance, and spend a little bit of time on wake frequency and strength calculations, what I think is one of the more important aspects of selecting a Thermowell. And then we'll finish up with talking a little bit about some of the testing and certifications that go along with Thermowells and some preventive maintenance. And then I put together a little selection checklist of things to know when you're specifying a Thermowell. So first off, why use a Thermowell? You know, temperature sensors are made to install directly into the process, but a lot of times they're not quite strong enough, or when you pull them out, it opens up the pipeline or the tank or whatever. And the addition of a Thermowell lets you change out that probe without having to drain your pipeline or tank. But probably the biggest, most important use of a Thermowell is just to protect that probe from either high flow rates or high viscosity fluids, or it might be a very corrosive or erosive medium that you have inside your piping. A lot of the stuff right at the beginning I'm going to go through pretty quickly because it's not real involved here. But, there are different types of Thermowell stems, which we've got the step tapered, straight sanitary, and then there are protection tubes, which I'm not going to talk about today because they're typically for thermocouples. Generally, they're just made from a chunk of Schedule 40 pipe or Schedule 80. And there's no good tight fit up between the temperature probe and the well. So it's a real, I guess what I would call kind of an inaccurate way of making a temperature measurement. Some illustrations here of what we mean by stepped and tapered. There's the stepped version is used for cases where you need a little faster time response. Tapered is kind of a compromise between the straight and the stepped. Connection styles, pretty much any kind of process connection, whether it's threaded, flanged, hygienic ferrules, they can be incorporated into a Thermowell. Some of the more common ones are the ANSI style flanges, pipe flanges. There are socket weld, weld-in, threaded, sanitary flanges, and then I guess what I'd call kind of almost a semi-custom that uses an O-ring to seal it into the process. Here we just show a variety of wells. This is an example of a tapered stem with a socket weld connection. And the next one right next to it has a Hygienic ferrule, and of course threaded, and then the large ANSI style flange. This would be a typical weld-in style Thermowell that would be used in a sanitary vessel. Drill a hole in the tank, weld it in place, polish the weld on the inside, and away you go. Here's a Hygienic ferrule or tri-clamp style connection with a straight stem Thermowell. And this one uses a tri-clamp or Hygienic ferrule connection for the instrument as well as the process connection. And this is typically done if you need kind of a quick disconnect, something that can be done without tools. Just release the clamp fitting and pull the device apart. And this is the O-ring style process connection. These are typically used in bioreactor vessels, and they're referred to by a few different names, but the Ingold name is one that, you know, the inventor of this, so that's has kind of stuck. A lot of different style process connections, like I said. Typically thread sizes are specified as an NPT thread, so they will seal as you tighten them up. The flanges, we need to specify a size and a rating. The flange sizes are usually done by class. Some of the more common ones are like class 150 and 300 and 600. And then excuse me, that would be the rating. The size would go by the piping, 1.5 inches, 2 inch, 2.5 inch. And then the gasket surface that goes on these will be either a raised surface or flat, or the last one on the list there, that RTJ, which is a ring joint, a little different style. But all these different size connections are available with Thermowells, and you know they can be specified for any of the 3 style stem Thermowell types. The socket weld are specified with pipe dimensions, so if you specify a 3/4 inch socket weld, the piece that welds into the socket on your piping actually measures 1.05 inch diameter, and that's the case for all the different pipe sizes. Like 1 inch would measure 1.315. Sanitary flanges or Hygienic ferrule, these are based on the tube size. So for example, the 1/2 and 3/4 inch tubing both use the same size fitting, and they're typically specified as 1/2 inch Hygienic ferrule or tri-clamp. Next, I wanted to talk a little bit about materials, and we're going to get into corrosion and erosion and how to minimize the effects of those, temperature ratings, pressure, fluid properties. Typically with materials, you want to match the Thermowell material to the pipe or the tank, and we'll talk a little bit about that also. First off, corrosion. There's a lot of tables available for recommended materials for the different fluids or chemicals and things that the Thermowell is going to come into contact with. This is just a small excerpt of one of the tables, and they include, you know, materials all the way from, you know, just regular carbon steel up to tantalum and hastelloys and all of the different exotic materials. And in addition to those, you will see some plastics listed, such as Teflon, Kynar, some other things like that will also be listed. And not choosing the correct material, you can really end up with some pretty bad problems. This photo shows the tip of a Thermowell with some pretty bad corrosion and kind of an impending failure spot right there where it's just about eaten all the way through the tip of the well. Now, erosion, on the other hand, can also cause well failures. There are several different materials available, and I've listed just a few of the more common ones here. Some of the stellite probably being the more common of these, which is just a essentially just a weld coating that's put over the, like a base metal Thermowell. It's a very hard material. It does really good erosion resistance against you know, particles such as I don't know, sand or like cement powder, those kinds of things. I had one instance where a manufacturer of granules for roofing shingles had called in and had a Thermowell that had been completely eaten away by those little gravel particles that you see on shingles, on housing shingles, and it actually eroded away the whole Thermowell and also part of the thermocouple that was inside the well. And curiously enough, the thermocouple was still giving a temperature reading. It wasn't the right temperature reading, but it was still working, which I guess really surprised me. It was enough of this material going by there to actually deform the thermocouple conductors so that they still were touching each other and still giving them some sort of a temperature reading. But the solution there was to supply a Thermowell with a stellite coating on it, and that solved their erosion problem. So in addition to the coatings and some of the exotic alloys, I mentioned that some plastic Thermowells are available. Probably the most common of those would be Teflon. We show a straight stem, pure 100% Teflon Thermowell. Some of the other things that are important to consider for corrosion applications is the surface finish. Getting a smoother surface finish, you're going to have less surface area available for the corrosion to start, and that may include electropolish and also passivation to eliminate any of the kind of foreign materials that might be on the surface of that Thermowell where corrosion could start and eat its way through the material. One of the more common ways of handling corrosion due to acids is with a tantalum oversheath on a straight stem Thermowell. This is a rather expensive option, but it does work really well. The basic Thermowell can be 316 or 304 or really any other base material that gives you the strength required for that particular application. And then the tantalum oversheath just slips right over it and provides the corrosion resistance.
And I think one thing to mention is that even though the tantalum sheath it can be an expensive option, it's much less expensive than if you make the entire Thermowell out of tantalum, which can be done as well, but it is significantly more expensive.
Yes, it is hugely expensive. And you also want to make sure that, you know, if you do specify some exotic alloy Thermowell and it's in a critical application, you know, you want to get the material certification for that, but you may also want to request a positive material identification. And this is done with X-ray fluorescence, and it will give the exact composition of that material just as another check, just to make sure that, you know, you're getting what you specified and it will be successful in that particular application. One of the, I guess what I consider one of the more important parts of selecting a Thermowell is to make sure that it's strong enough to survive the process. And And that goes back to the material selection, and also, more importantly, with the dimensions of the Thermowell, like the immersion length, the diameter. And there's always a balance between the immersion length and the strength of the well. If we have a well that's too short, we're going to have some stem conduction error. If it's too long, the well could start to vibrate due to wake frequency issues or strength problems. If it's a really viscous product, for example, and it's flowing by at a pretty good rate, the well might not be strong enough to withstand that. So there's a balance between these, and we're going to go into this in a little bit more detail here. First thing to look at, though, is the wake frequency and strength calculation. And this is a little excerpt from the ASME website, and really the only reason I put this up here is just to demonstrate that it was updated in 2010, and it's quite different than the old standard, which had been around like for decades. And it does a much better job of giving you an accurate picture of how that Thermowell is going to perform in your process. We have a little diagram problem here. This is supposed to show a wake frequency, and for whatever reason, it didn't come through on the WebEx. So anyway, if you go to, if you can actually Google wake frequency, and you'll come up with actually a little demonstration of what happens when the flow rate is too high going past a cylindrical object, or actually any object in a flow. And what happens is that these little eddies will form right behind the Thermowell, and if the flow is high enough, these little eddies will detach, and they alternate from side to side. And the frequency of that alternating vortices, they will cause a vibration in the well if that frequency matches the resonant frequency of the Thermowell. And we can see by looking at a table here, or this little chart, of where that flow rate is in relationship to the design of the Thermowell. One of the more common Thermowell sizes uses a 3/4 inch NPT connection. And you can see from this table that we have about 250 feet per second as a safe flow velocity for a 4-inch immersion length. Compare that to a 1/4 inch diameter direct immersion sensor, and we're only at about 30 feet per second, roughly. So this is really an important aspect of selecting a Thermowell. Some of the information that you'll be asked to provide, we need to know what fluid it's in, the temperature, the style of Thermowell. Although if you don't, well, I guess it would just be kind of the process connection for the Thermowell. We can play around with the stem type to provide something that will work in your particular process. So, but these are some of the things that you're going to need to know to get a good, accurate wake frequency and strength calculation. And if you don't know some of the parameters, we can certainly make some fairly close guesses at what's going on. But you maybe will want to put a little more conservative number associated with that type of calculation. And to kind of get you in the right ballpark, there are some Thermowell manufacturers. This one happens to be Alloy Engineering that supplied some tables for this presentation. And they have a few caveats surrounding all of these, and with the most important one being that these tables are just to be used as a guideline, and you don't want to use these as the absolute gospel for choosing a the correct Thermowell and immersion length for a particular process. These are just to kind of get you in the right ballpark. And I've highlighted a couple numbers here just to compare it to a tapered stem. This is the stepped stem, and we can see, I'm looking at the unbracketed number here, which is 128 feet per second. So this would be typical for like steam, and 71.2 feet per second for use in water at 4.5-inch immersion length. And this would be the 3/4-inch NPT threaded connection, and either in 304 or 316 stainless steel. So there's a lot of different variables that come into play here. And if we look at the same immersion length and material for a tapered stem, we can see that these numbers jump up about, roughly a third again as much. So we're 197 feet per second in steam and 135 in water. And if you were to go to a straight stem version here, the numbers would increase just a little bit, but really not a whole lot.
So Bill, along those lines, is there a recommendation that you have as far as where you would start with the well type? Do you start with a straight, and if that works, great, or would you right away go to a tapered, or how do you kind of approach that?
You're going to get my generic response. It depends on what you want to do. There's a lot of factors that come into play in selecting that, and probably the best place to start would be with what the process is going to require. Do you have a time response issue where, if that's the case, if you want something fast, you'd start with a stepped stem. If you need strength, I'd start with tapered right away. If there's erosion or corrosion, the straight stem would be a good place to start. So, and then, again, there's this balance between picking an immersion length that's long enough to get a good accurate measurement, but not so long that you fail the wake frequency calculation. And if we do, if we don't do this wake frequency calculation accurately enough, and if you just don't bother with it, you can actually fail these Thermowells, and they will start to vibrate and they will break off and cause trouble. This one, curiously enough, has what they call a velocity collar on it, and that's to shorten up the actual length of the well that's exposed to the fluid. But the new version of the wake frequency equations and calculations do not allow a velocity collar, and the reason for that is that they don't really ever fit up tight enough in whatever they're inserting into, and the well can still vibrate in there, so they really don't account for those anymore. Here's a little closer shot of what happened. The little pink highlight is where the crack is. Kind of formed in a rather interesting shape, I think. I suppose that was because of the way the well was vibrating. And this one didn't get to the point of complete failure, but it did cause a crack right in that flange, which pretty significant. So the immersion length with a direct immersion RTD, we like to see at least 10 times the probe diameter plus the sensitive length of the probe. So for example, a 1/4-inch diameter sensor with a 1-inch sensitive length would need about 3.5 inches of immersion to get a good, accurate measurement and avoid stem conduction errors. And that's just kind of a generic statement in most fluids. In air temperature, that's going to be probably off by a factor of 10. But for Thermowell applications, we need about 4 to 4.5 inches of immersion to overcome most stem conduction issues. If we look at this table that we put together, and this measures the effects of immersion on a tapered stem Thermowell with an RTD installed in it. And it was done at 3 different temperatures in an ice bath, 100 degrees C, and 200 degrees C oil baths. And the probe was slowly lowered in, starting at 0 inches, and just slowly immersed. So that's along the x-axis here, so we got 2 inches and 4 inches. And the error is expressed as a percentage of the delta T. So we're doing this in room temperature, and we can see that for a roughly 2.5-inch immersion Thermowell, we have about roughly 3% of that delta T. So if we're in our 200 degrees C, well, we'll pick 100 degrees C just so the math is easier. We got about 3 degrees C of error there, so 3% of 100 degrees. Let me back up. 20 degrees C, so it's 3% of 80 degrees C. That delta T difference is our error, so it's about 2 degrees C, which for some processes can be pretty significant. When we get out here past 4 inches, most of that stem conduction or immersion error has gone away. So I always recommend that if we can get at least that much immersion, you're going to get a good, accurate temperature reading. But then again, if the process is not going to, if you've got a high flow rate or it's a really viscous product or both variables are present, then we need to shorten up that well, or we need to beef it up, maybe go to a larger diameter, maybe go to a tapered stem rather than stepped or even a straight stem. So there are things that can be done to still maintain that immersion length and make sure that the well is strong enough to survive in that process.
Say, Bill, we've got a quick question here. If you could maybe just explain a little bit more about stem conduction. I think you touched on it, but if you could maybe just go back, I think it was one of the first slides or a couple slides ago, and just touch a little bit more on exactly what stem conduction is.
Okay, well, I guess maybe what I'll do, we'll start here. With stem conduction, if the process fluid and the ambient conditions are the same, we're not going to see any heat flow through the metal parts of the Thermowell or the temperature probe or even the lead wires that go from the connection head down to the sensing element. But as soon as we have this temperature difference, our example here shows a 200 degrees C process fluid in a 25 C ambient condition. You're going to have some heat flowing around in here, and the ambient conditions are going to have a cooling effect on the sensing element, which is down in this area. And now if we maintain a sufficient immersion length, that heat from, or that cooling effect will dissipate before it hits the sensing element, and you'll still get a good, accurate measurement. But if you have too short of an immersion length, you are going to see some conduction error.
Okay, thanks, Bill. Appreciate it.
One of the ways to get around the immersion issue in really small diameter lines would be with an elbow-style Thermowell. And this allows the installation of a Thermowell, which is in this enlarged section of the tubing here. This happens to be 3/4 inch tubing. And this section around the Thermowell is flared out so that it doesn't restrict the flow. So you still have the same cross-sectional area for the fluid to flow through this elbow-style Thermowell. So it's a real good solution for smaller diameter lines, and these are made up to probably, I think, 4-inch tube diameters. Another way to get around that, here's a little cross-sectional view of that elbow Thermowell. So it's typically installed with the fluid directed right at the tip of the sensor, just to make sure that we don't get any dead spaces in here. And then you have good clean flow going around the bend in that tubing. You can also use just regular pipe tees. This shows a sanitary tee. And for this type of an installation, what we like to see, you can either go through the outlet of a tee, which is an okay way to do it. You still have kind of a bit limited because there's going to be a little bit more force on this sensor and a little more opportunity for wake frequency issues with it. A little better way to do this would be with the flow coming up from the bottom and hitting it. The drawback to this is that you do get some dead space back in here, so it's not going to be flushing out that material. Really the best way to put it is so that the flow is coming directly at the tip of the sensor, and that tends to wash out this area. And because the fluid is flowing right at the tip of the sensor and it's real turbulent in here, the wake frequency and strength issues become much less of an issue. And this, you can kind of make your own story about what was going on here. This was a photo that was supplied to us from Alloy Engineering of somebody that sort of installed a Thermowell backwards, and I'm guessing that they're going to have a lot of stem conduction with this one. So.
Not to mention, I'd like to see them get the sensor in there. That might be the more difficult part, but
yes.
Just goes to show there are some simple things that you can do to increase your measurement confidence, and one of them would be to install the Thermowell correctly. It certainly helps.
So I talked a little bit about time constant, and here's some numbers that we've come up with for Thermowells that are in water moving at 3 feet per second. And these would have kind of a typical 100 ohm platinum RTD installed in them. And the time constant, I've got a little definition there. It's the time it takes for the sensor to respond to 63.2% of a step change in temperature. So if we're taking that temperature sensor from 0 degrees C to 100, what we're saying is it's going to take 22 seconds for it to get up to 63.2 degrees C. And of course, the more metal we add around that temperature sensor with a tapered well, it's going to take a little bit longer, and then up to 30 seconds for the straight stem Thermowell. And some of the dimensions on these, this section here is 1/2 inch diameter. This one tapers from roughly 7/8 down to about 5/8. And the straight stem Thermowells, pretty common standard there would be just 3/4 inch diameter. One way you can speed these up, if your temperature range allows it, would be to add some sort of a heat transfer paste in the well, and that will significantly cut the time constant. Most of the heat transfer paste materials are limited to about 200 degrees C. So there's not a lot of good options for temperatures over that for a heat transfer material. Now, if you still need a Thermowell and you need fast response and the wake frequency and the strength will allow it, there's a fast response tip Thermowell that uses a special temperature probe with an 1/8 inch diameter tip. And this section is roughly, I think it's 0.2 inch diameter maybe. So it's a pretty thin wall. Can be kind of fragile type assembly. But it does have a 4-second time constant when the probe is installed with a heat transfer paste. One thing that I haven't mentioned yet is the importance of spring loading. This particular sensor happens to be spring loaded. There's a spring inside this threaded fitting. And the purpose for that is to make sure that the temperature probe is bottomed securely in the Thermowell. And it does a couple of things. One is that it keeps the probe from vibrating inside the well if the process has any kind of vibration going on. It also and it's kind of a minimal help, but it does keep the tip in contact with the tip of the well, so there's going to be a little better heat transfer right through the tip of the temperature probe. Another example of a specialty Thermowell, this one had a perforated stem so that the fluid would pass through it. And here's a larger style elbow Thermowell. There you can see the actual 3/8 diameter Thermowell inside. And I think this is probably like in a 4-inch sanitary style tubing. So some of the definitions of the different letters and variables that are used to specify a Thermowell, and these are pretty much an industry standard that you'll see on instrument data sheets. The process connections usually specified as the letter P, and then immersion length is the U, and the lag length T. And one of the more important ones would be the A dimension, which is the bore depth. And some other types there. Instrument connection, usually a female 1/2-inch NPT, although what we saw earlier is that hygienic ferrules are also available. Then I want to talk a little bit about some of the materials, bore diameters, and some of the other testing and certifications that go along with Thermowells. Our diagram here shows where all these letter variables apply. U being the immersion length of the well, this would be the wetted surface, and T being the lag length. And this is in addition to the standard for threaded wells. It's usually about 1 3/4 inches. That includes the thread and a wrench hex, and then the lag extension is in addition to that. And you may want to specify this if you have an insulated pipe that has, let's say you have a 3-inch insulation blanket around that pipe, you maybe would want a 3-inch lag extension so that you can more easily get a wrench on it and attach the instrument to it. P specifies the process connection. And again, the most important one that you need to know when you're specifying a temperature probe is the bore depth. And that's usually this overall length minus the thickness of the tip, which is typically a 1/4 inch. So with this number, the probe manufacturer will be able to select the correct length temperature probe for the Thermowell. I touched on this earlier, thread sizes, usually an NPT, and the socket weld sizes, again, are in pipe sizes. So 3/4 inch does not necessarily refer to the OD of the connection, but the connection is based on the pipe size. So it actually measures 1.05 outside diameter. And the different flange sizes, and these go all the way up to, I think, class 2500. There may be some other ones there, but usually from the class 150 on up to 2500 would be the most common classes of flanges. And as far as the size, anywhere from 1 inch on up to about 3 inch would cover most of the applications that I run across. There are smaller and larger sizes available. And in the hygienic ferrule or triclamp size, one thing to remember here is that the 1/2 inch and 1 inch hygienic ferrules are the same size fitting. So if you specify 1/2 or 3/4 inch triclamp or hygienic ferrule, there's probably only going to be, the manufacturers are only going to use one code letter or number for that, but it does cover both of those. And the same thing holds true for the 1 inch and 1.5 inch tube sizes. It uses the same size fitting for those. All the other sizes have a unique ferrule size for each tube size. So some of some of the soft items that go along with the hardware would be all the testing and certifications that are available. And I've listed just a few of the more common ones here, with the wake frequency and strength calculation being the most important and the most common of these. And next would be that material certificate. Some of these apply to like the animal-derived materials. Usually that's specific to the pharmaceutical or food beverage industries. And some of these, like a weld map that shows the location identification of every weld that's done on the Thermowell. For example, if it's a flanged Thermowell or one of the elbow-style Thermowells, if it's a real critical process and you need to know that you've got really good welds and it's the material that it's supposed to be, and you may want to specify this weld map option. So there's just a whole bunch of these, and like I said, this is probably not even half of what really is available. So in addition to those, there are some different options that can be specified with Thermowells, and again, these are just some of the more common ones. Anything from having the manufacturer put a tag number on it, or cleaning it for service in oxygen, because you want to make sure that all the oils and foreign materials are removed from that Thermowell so that you don't get any contamination and any kind of, flammable comes to mind when we're doing oxygen service. So you want to make sure that all that stuff is cleaned away. One of the ones that is common for flange Thermowells would be a full weld penetration where the flange is welded to the stem of the Thermowell. And that can be certified, and also usually when that is specified, I see customers requesting either an X-ray inspection or even a dye penetrant style testing, just to make sure that it's not cracked and that it's got a full penetration weld.
So, Bill, we've got a couple of questions here. One is, why are wells only used with thermocouples and not RTDs? I guess it's like the answer to that is they are actually used for both. So we apologize if that wasn't made clear. Yeah, Thermowells are used with thermocouples as well as RTDs all the time. Really, any type of temperature sensor could be used. You could have a bimetal thermometer that goes into a Thermowell as also. It's there to protect the sensor is really what it's doing. And then another question, Bill, is what is the potential failure mode of a thermocouple or an RTD without a Thermowell? So if you don't have a Thermowell at all, what are the issues that we typically see that would, I know you covered a lot of them up front, but what are some of the more common failure modes that you see if you don't have a well?
One of the more common ones would be that the probe would either bend or break off, and I see that probably most commonly in, for whatever reason, food and beverage applications, where one example would be that we had a customer that was pumping pudding through a pipe at a pretty high flow rate, and you can imagine how viscous that stuff is, and then they're trying to pump it through this pipe just as quick as they can. Quarter-inch diameter direct immersion sensor in that case just bent right over. I don't think that one actually broke off, but it did bend. And if it does break off, nothing good comes of it, because there's usually a pump or something downstream of it that's going to get damaged pretty badly. So you really want to make sure that you've kind of done your due diligence there and made sure that it's strong enough. In that particular case, the solution wasn't a separable Thermowell. It was just to provide a direct immersion style sensor that had a stepped stem design, which went from a 1/2 inch diameter and stepped it down to a 1/4 inch. Although a Thermowell would have been an acceptable solution for that particular application, it would have provided enough strength, and probably more strength, more so than the direct immersion style sensor. It was, time response became a little bit of an issue with that particular application, where it was the Thermowell that was strong enough to withstand that flow, and then the separable RTD or a thermocouple just wasn't fast enough to provide for that particular process. So we ended up going with that direct immersion style sensor. And one of the other type of issues that can come up is with corrosion or erosion. Anytime you have, especially corrosive items, a direct immersion style probe, the wall thickness on those parts is usually pretty thin, and it just isn't going to last very long in a corrosive environment. Let's see. Oh, I wanted to mention a little bit here about maintenance. There's really not a whole lot to it, but some applications, especially in test wells, you may get a buildup of stuff inside there over time. You want to make sure you clean that out so that you have good heat transfer between the probe and the thermal well. And if you're using a heat transfer compound in the well, that you renew that after pulling the probe out and calibrating it or replacing it. Some processes will have the, might be a product that will adhere to the well a little bit, make sure that that has not happened. I have had applications where the complaint is that the time response has slowed down over time, and they pull the Thermowell out and they find that there's a 1/4 or a 1/2 inch coating of whatever stuff was in the piping just glued right to the well, and so that can be a bit of an issue. And then finally, make sure that the RTD bottoms out in the well and that the spring loading is working. Most of the time it should compress about a 1/2 inch, and that's usually sufficient. And then of course check for leaks, and in the case of a flange, you might want to make sure that there's no visible cracks. So, and finally today, just running down a little Thermowell selection checklist. These are just some of the things that you want to consider when making a Thermowell selection. And again, to get back to a question we had earlier about, where do you start with this? And I guess I would probably start with the material, because that's usually one of the easier things to pick. It gets a little more difficult as we go down the list here, where the process connection. You've already got that just by the style of the piping that you're installing this into. It's already defined. But then when we get down to the wake frequency and the immersion length, and then picking the surface finish and the time response, those are the things where, kind of the most thought has to go into that. And I would, don't be reluctant to reach out for some help from the temperature assembly manufacturer in selecting that, because there is a pretty delicate balance in between that wake frequency and the immersion length to get a good, accurate measurement that is going to have the time response required for your application. So I guess kind of the most important things that I want you to walk away with today is that make sure we select the right materials, coatings, and the surface finish for the Thermowell. Do the wake frequency and strength calculations if there's any doubt about whether it's going to be strong enough. Pick a good immersion length and consider the time response. Then, of course, there's always the paperwork that goes along with the well, and we need to have the correct testing and certifications, especially if you're in kind of the food, beverage, pharmaceutical world, even some chemical processes. You need to know and track that kind of stuff. And then when you're specifying a temperature probe for a Thermowell, you know, whether it's a thermocouple, RTD, a bimetal dial thermometer type thing, or even an older liquid in glass thermometer, we need to know the bore depth of the Thermowell so that the correct length temperature probe can be selected for that particular well. And I guess with that, I'll turn this back over to Jeff and see if we have any more questions.
Okay, thank you, Bill, very much. We do have a few minutes, and it looks like we've got a few questions. If you do have questions, go ahead and type them into the Q&A section or the chat box, and we can get them answered for you. If you have a more detailed question, more specific question, go ahead and contact us at the information or at the address or phone number that's on the screen right now, and we'd be more than happy to help you out. A couple questions, one regarding you kind of mentioned heat transfer compound, and somebody was just wondering, you know, specifically, what do you recommend, and what are the benefits of using that compound in a Thermowell?
Well, there are some good features of it and maybe some bad ones. I'll start out with the bad. If you've got a really cold process and you put heat transfer paste in there, chances are if it's not suitable for the cold temperature, it could actually freeze the probe in. And if you have a failure, or if you need to pull it out for calibration, it's going to be stuck in there pretty good, and you're not going to be able to get it out. So that needs to be taken into consideration. But on the positive side, it can help prevent any kind of corrosion from happening inside the well. If it's maybe it's a carbon steel well and something gets in there, some water or whatever, it may help prevent some corrosion inside the well. But really the main benefit of using heat transfer paste would be to speed up the time response. And again, it's going to take that roughly 26-second time constant that you would see in a tapered stem Thermowell, and it'll trim it down to, probably somewhere in the high teens, around 17, 18 second time constant. So it does make a pretty significant improvement in the time response.
Okay, and then one other comment had to do with, I think, going back to what are some of the failure modes or common failure modes, and the one that was mentioned, Bill mentioned kind of with bending was one of the failure modes, and usually where we see that is when the length of the sensor starts to get longer. Although a direct immersion from a temperature measurement perspective, we would always like to have a direct immersion sensor because that's going to give you the best temperature reading. There's a lot of times where that's just not practical, and one of those is as the length of the sensor gets longer. If it's just hanging in a static tank, that's usually not an issue. If you've got some kind of flow, that's usually when you start to run into problems. So anytime your sensor gets longer, you want to start thinking about, do I maybe need a Thermowell for this to protect that sensor? The other one where we see a lot in biotech and pharma applications is they put in a Thermowell not because they couldn't use a direct immersion, but because they prefer to keep the system closed, and they don't want to, when they replace a sensor or they calibrate a sensor, they don't want to have to open up that system. They want to keep it all closed, so they can just pull that sensor out and not have to worry about anything coming out of the system, or probably more importantly, any foreign contaminants going into the system. So it's another reason that a lot of folks use different types of Thermowells. So with that, it doesn't look like we've got any additional questions. Again, we would be happy to answer any. If you think of something later on, go ahead and shoot us an email. And also just want to remind you, we do have some upcoming sessions in next month, I guess it is already. We talk about wake frequency and strength considerations, both in Thermowells as well as direct immersion applications. Then in April, we're looking at how to improve accuracy in biopharma processes, and in May, RTD accuracy and associated error sources. So certainly we would love to see you back at some of those sessions. There will be reminders sent out within the upcoming weeks and months on those. So with that, if we don't have any other questions, thank you very much for joining us, and we look forward to seeing you next time. Have a great afternoon.
Yep, thanks for tuning in.